Hey everybody, welcome. Today I'm going to break down the essentials of what you need to know when you're studying acids and bases. And this is great review if you're in an AP chemistry course, college course, or just a general chemistry course. Now let's go ahead and get started. So there's three different ways you can define acids and bases. The first one is the Arrhenius and acid and base. Now what Arrhenius said is he said that acids produce H+. So when you put an acid into water, it's going to produce H+ ions. And so a perfect example of an Arrhenius acid is something like hydrochloric acid, because when you put that into water, it's going to completely dissociate into H+ and Cl-. Another great example of an Arrhenius acid would be nitric acid. Now this is going to dissociate into H+ and the nitrate ion. So the definition for an Arrhenius base is something that's going to ionize to produce OH-. So this is something simple like sodium hydroxide or calcium hydroxide. So both of these are going to ionize into their separate parts. So you got your hydroxide ion and your sodium ion. And in the case of calcium hydroxide, you have your calcium 2+ ion and 2 hydroxide ions that are formed. So the Arrhenius definition is the simplest form of an acid-base definition. The next one that you're going to need to know is called the Bronsted acid and base definition. Now, what Bronsted said is that acids are proton donors and bases are proton acceptors. Now, this differs from the previous definition, especially in the case of a base. In the case of the base, he said that bases are something that produce OH-. Now, Bronsted said it a little bit differently, and he said that bases are proton acceptors, meaning that they take a proton from something else. Now, a good example of a Bronsted acid would be something like HBr, and a Bronsted base would be something like ammonia here. So you have HBr plus NH3. This is going to produce the ammonium ion and bromide ion. So this is a great example of a Bronsted acid and a base. So you can see what's unique here is when you're looking at acids and bases, you always want to consider that when you do an acid-base reaction, you're going to produce a conjugate acid and base on the other end. So for example, if you look at the green here, you have your HBr. That is an acid at the start. Once it completes the reaction, it forms the conjugate base, which is bromine minus. Now, this part, the bromine minus, is not acidic anymore. It's now considered to be a conjugate base. You look at something like ammonia here, that's your base on the reactant side of the equation. And when that goes through to do its reaction, it produces ammonium, which is NH4+. That is now considered to be a conjugate acid, because if you look at it, it's something that can now donate a proton potentially. So an example of this is if we take just acetic acid and we react it with water, we want to identify what's the acid, what's the base, the conjugate acid, and the conjugate base. So we can do this really simply by just looking at what's able to donate a proton. Now, the thing that's able to donate the proton in this case is the acetic acid, has the word acid in it. So and it has the free proton at the end of the COOH there. Now, what is the thing that is accepting the proton? In this case, it would be the water, and so that would be defined as our base. Now, what we would want to do next is we want to pair up the acid and the conjugate base pair. Now, whenever you have an acid on the reactant side, on the product side, it's always going to produce a conjugate base. So in this case, the acetate ion, the CH3COO-, is going to be the conjugate base. Now, the thing that we started with on the reactant side, that was the base, that's our water, that's always going to form a conjugate acid on the product side. So that's going to be our hydronium ion, our H3O+. So if we look at another example here, we have water reacting with ammonia to produce ammonium and hydroxide. Now this, we want to identify what's the acid, what's the base, what's the conjugate acid, and what's the conjugate base. Now this is a great example because in the previous one, you saw that water was acting as the base. Now in this reaction, we have the opposite. Now water can act as an acid. And this is one thing you want to remember is that compounds can either act as acids or bases just depending on the conditions that they're in. So in this case, the water is the thing that's actually donating the proton to the ammonia. So we would say that that's our acid. And our conjugate base would be the hydroxide ion on the product side. Now, since the ammonia is accepting the proton, we would consider that to be the base. And the conjugate acid would be the ammonium, the NH4+. So this is a really common problem that you're likely to get, is identifying what's the acid and the base, and then also identifying what's the conjugate acid and base on the product side. Now the third and final definition for acids and bases would be the Lewis acid-base definition. Now, one thing that you want to remember is that Lewis said that all Bronsted acids are actually Lewis acids. Now, where he differs in his definition is that he says acids are electron pair acceptors, meaning that they're capable of accepting a pair of electrons from something else. In that case, that would be the base. Now, he says that bases are electron pair donors, and this is something that's able to donate an electron pair to something else, and that something has to be an acid. So let's look at an example. So in this case, we have NH3 and BF3. Now, one thing you remember from NH3 is that you have a lone pair on the nitrogen. Now, this lone pair can act as a base. It can donate to something else. And in this case, we have BF3. And if you remember from our electron configuration that we did previously, BF3 does not have an octet, so it's actually able to accept an electron pair from something else. In this case, it will be from the ammonia. So the ammonia can then react with this BF3 to produce what we call a Lewis acid-base adduct. And so this is going to be what we see with the Lewis acid-base definition. Now let's look at what are some definitions for strong acids and strong bases. Now, strong acids are this list here. You have perchloric acid, HCl, HBr, HI, nitric acid, and sulfuric acid. The one thing that you'll notice from this list is that they contain the series of halogens except for fluorine, so there's no HF on this list, and they contain things that are easily considered Arrhenius acids, so they're able to donate a proton to something else. Now, if we look at the list of strong bases, we got lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium, strontium, and barium hydroxide. So these are things that are readily soluble in water, and they have an OH that when it dissolves, it just forms OH in the solution. So these are something that's considered to be a strong base. Now, what about strong bases and strong acids? So one thing to keep in mind when you're looking at things that are strong acids or strong bases is that when we draw the equilibrium arrow, it's always the straight arrow pointing to the product side. We never have an equilibrium going to the left side. And the reason for that is because by definition, strong acids and bases completely dissociate when they're in solution. So they form all on the product side. Now, this is going to be different from weak acids and bases, which do not completely dissociate. And so what we do when we write out equations for a weak acid, we would write an example here where we have HA is on our reactant side, and we use the equilibrium arrow. So it's going both to the right and the left, and it produces the H plus and then A minus. So the A minus is the conjugate base, H plus conjugate. So in this case, we have an equilibrium K that we can solve for this. So we have our equilibrium equation would just be the concentration of H times the concentration of A divided by the concentration of HA. So this equilibrium equation is what we'll use later on to determine actually the pH of things, so how strong of an acid or a base a certain thing is. And so for a base equation, we would just have our base plus water produces our BH plus, which is our protonated form of the base, and it produces OH minus, so it deprotonates the water there. And the same thing that we had for our Ka, we can do to find the equilibrium constant for the base. So we have our equilibrium constant for the base is just equal to BH times OH divided by the concentration of the starting base. And so we can use these two things, and we'll go over that later, on how we can actually use them to find the pH or the relative acidity of our compound. So thanks for joining. In the next few lessons, I'll share some more information on how to solve problems with acids and bases, how to do titrations, and a lot of that other stuff. If you have any questions or comments, please post them below. Thanks for joining. Have a great day.